Now axis. Okay, this is a little tricky. I'll try my best, but if you guys have any questions, just let me know, okay? So like we already said, the impulse of the heart is going from the top to the bottom, right? It's usually going in a sort of a 60-degree angle, exactly. So you have, so you know, in math, you would get those graph papers and draw out graphs. So literally this is what it is, okay? So you have lead 1, which is at 0-degree angle, and then just take another angle, which is AVF, which is at 90 degrees to lead 1. Okay, so in math we had all drawn that, right? We had all drawn one x-axis and one y-axis. So now when the heart is depolarizing, it's for easier sake, the predominantly it's depolarizing in this right lower quadrant, okay? I mean left lower quadrant of the body, but right lower quadrant on the screen. Okay, so your impulse mostly lies between 0 and 90-degree because the heart is depolarizing towards the LV from top to bottom predominantly, right? And that can encompass anywhere between -30 to +100. That's normal axis for the heart, okay? So anywhere between, if your vector lies, the R wave vector lies, that's your normal axis, and we'll see a little bit more. Now, for some reason, let's say the axis of the heart, instead of lying in this quadrant, let's say lies a little more to the right of this, okay? So let's say it lies anywhere between 90 and 180, okay? So that is called as right axis. That's where the right ventricle is. That is called as right axis deviation, okay? So anything over 100 or 110 up till 180 is called as right axis deviation, and we will talk about how we came up with 100 and 110. Anything in the top left, basically between -30 and -90, is called as left axis deviation. Okay, and then anything in the rest left out quadrant is called as extreme left axis or northwest axis. Okay, so right axis, normal axis, right axis, left axis, and extreme left, or also called as the northwest axis. Okay, and let me tell you what I mean by that. So then when we look at an EKG, yeah, we'll have to pull up an EKG here actually.
So let's go to this one.
Yeah. So now looking at the EKG, so we talked about lead 1 and lead AVF. We've already mentioned, okay, the chest leads don't make any perpendicular axis with the heart. You cannot use those to calculate an axis, okay? You can only use the limb leads to calculate an axis. Now, when you look at lead 1, it makes an angle of 0-degree with the heart. And when you look at lead AVF, it makes an angle of 90 degrees with the heart. That means if the impulse is in the left lower quadrant, your AVF should be positive and your lead 1 should be positive, right? Ideally.
So let's calculate the axis for this ECG. Look at lead 1, count the number of squares in the positive deflection in the QRS axis. If you look at it, if you look carefully, it's probably 5 squares because this is a big square here, plus another couple here and a couple here. So if you probably count them, it will be probably, let's say, 9 small squares in the positive direction in the vertical axis. If you look at AVF now AVF, what is the direction of this? Most predominantly, this is a negative complex, and this one was a positive complex. This entire thing was positive in lead 1, and this is negative in AVF. Let's calculate how much negative. We have about 3 squares ऊपर, 3 के नीचे 5 और 5 10. So we have about 13 negative squares and let's say about 3 or 4 positive squares. So अगर हम resultant निकालेंगे तो 13 minus 3 we will get practically about 10 in the negative direction. So remember AVF में 10 in the negative direction, lead 1 में you had 9 in the positive direction. So far with me? We go back to this diagram that we have. Let's erase whatever we have already written on this. So you remember, if you remember how much was the positive deflection in lead 1. Bhavya, can you tell me? Your mic is unmuted, so you should be able to tell me. No, she doesn't want to. Prakhar, I'm unmuting your mic. So can you remember what was the positive in lead 1? What was the positive deflection in lead 1, Prakhar?
So 0 degree, along 0 degree.
No, it was 9. Abhi count kiya na? There were 9 small
Okay,
squares
yeah,
in the
sorry.
positive. So this is
Yes,
the
sir.
positive direction here. And just make a sort of a small graph paper on this. 1, 2, 3, 4, 5, 6, 7, 8, 9. So here you have practically 9 small squares in the positive direction on lead 1. What about AVF? This is the positive direction of AVF. We counted that our resultant vector there was how much? Prakhar?
Sir, it was 10.
Minus 10.
Yeah, minus 10.
So this is the positive direction of AVF. So we have to draw in the negative direction of AVF. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So practically this is what the vector we get here in the negative direction for AVF. So you got this? So far so good,
Yes, sir.
Prakhar? Let's
Yes, sir.
make this complete square. अगर हम इसको वापस join करेंगे और इसको extend करेंगे, so this is what we get if we make this square in AVF and in lead 1. अगर AVF में positive होता तो हम इस तरफ बनाते towards the positive direction of AVF, but AVF में negative था इसलिए हमने उल्टा बनाया. Now if we have
Yes, sir.
completed the square, we just let's complete the resultant vector. So resultant will be this one. तो रिजल्टेंट कहाँ जा रहा है? प्रैक्टिकली 30 और 60 के बीच में. So it's approximately, let's say, about 45. So the axis of our ECG is minus 45 degrees. And we said anything which is left of minus 30 will give you a left axis deviation. So if you go back to that ECG, हमने अभी पहले भी कहा था that we were using all these criteria. We said this is LVH. LVH is likely to have a left axis deviation. If we calculated the axis now, we came up to minus 45. So which is also corroborates and confirms to whatever we were just saying. So it's the easiest thing to do. If you have a graph paper in your mind, find what is the resultant in AVF, find what is the resultant in 1, and just make those two vectors, make a resultant vector, you will always get the right number. Kunal.
Sir, I had a question.
Yes, I know, Prakhar. We'll come back. Okay, go ahead, Prakhar, ask.
So in that particular ECG you just showed, so do we have a particular approach to which lead we begin with? Like we begin with lead 2 for the rate and rhythm. So in this we directly went to V5, V6 and V1 to look at the length of the leads, to add up the length if they added more than 35. So do we have a particular approach to that ECG?
Yes, so when you have to look for the rhythm, the lead 2 is so in the bottom of the ECG, you will get a long lead. That is always there. If you see this. Now this one is lead 3, which is giving you only 2 complexes. AVF, which is giving you 2 complexes. But here you've got this lead 2, which is giving you the longest strip. So when you want to look at the rhythm, this is the best you use. That's what you use. If you are looking at the P waves, the P wave vector is always coinciding best with lead 2. That is why whenever you want to talk of lead of the P wave, you look at lead 2. When you were talking about hypertrophies, then we said we look at V5 and V6 and V1. That is because those are the particular leads which are looking at those chambers in that area. We want to look at the left ventricle, we want to look at the left ventricular wall. That's why we approached the V1 and V5, V6 when we were trying to look for hypertrophy. Now, when we were trying to look at the axis, it's the easiest to get the axis in 1 and AVF, because 1 we all remember is 0 and AVF is 90. So that's, you can calculate in any of the other leads. It will give you the same answers, but it's easiest in 1 and AVF. That's why I chose 1 and AVF. Does that
Okay.
your
Yes, sir. Thank you.
okay. Sonal, sorry.
Yeah, no. So exactly. So just remember that one. So just simplifying this, what you can remember is once you have lead next slide. Once you have lead one and you have AVF. So whenever one is upright, okay, predominantly upright, and AVF is, so both of them, the R is more than the S, okay, predominantly upright, that means it's normal axis. Same thing, if one is upright, but AVF is predominantly negative, that means one is pointing up, AVF is pointing down, so they're leaving each other, so left leaves. So one up, AVF down, they're leaving each other, left axis. If one is down and AVF is up, that means the two complexes are reaching each other. So right reaches the right axis deviation. And if both of them are negative, there is something seriously wrong, and that's extreme left axis. So either you've put the leads completely wrong or the patient is in deep trouble, okay? So normal axis, both upright, left leaves. So one is up, AVF is, so one is always on top, AVF is always on bottom. So if they're leaving each other, it's left. If they're reaching each other, it's right. And if they're both negative, it's extreme left. Yeah.
Fair enough. We have again two hands, Bhavya and Prakhar. I'm going to skip the hands because it's already 7:50 here. We should be winding up and we have a little bit more to go. We will take the questions after we are done with this. So this was another ECG which asks what is the axis in this one. So if we
Okay,
look at one,
yeah. We'll just simplify it, okay? One is up, AVF is up, both of them are predominantly positive, normal axis.
Yes, so both are pointing upwards, normal axis. Supposing this would have been down, the QRS complex down, and this AVF would have been up, that means 1 and AVF are reaching out to each other, that goes in for a right axis deviation. Supposing this was up and AVF was down, then it would have been that AVF and 1 are leaving each other, that comes to a left axis deviation.
And then the last thing I'll talk about from the QRS is the QT interval, okay? It's basically ventricular depolarization and a little bit of the repolarization starting. Now, so this is basically from the onset of the Q wave to the end of the T wave, okay? Not the beginning, but the end of T wave, okay? So QT interval. So what you're, yeah. So beginning of the QRS to the end of the T wave. And what you typically do is you draw a slope across the T wave, right? So you draw a slope across the T wave, and wherever that slope meets the baseline is where you take the end of the T wave, okay? Because T wave shape changes and it becomes harder. So what you do is this QT interval changes a lot with the rate, okay? Basically what it's the hard depolarizing and repolarizing. So whenever the rate will change, this interval will change. So what we have come up with is the corrected QT, it's called QTC, or the corrected QT interval. And we have this common formula, the Bazet's formula. All you do is QT divided by square root of RR. You just have to memorize this for now. Okay, and what you look for is the QTC interval. And normal is less than 440. Ideally, it differs a little between males and females and, you know, by age, younger people and puberty and this and that. But normally it's less than 440 milliseconds, and it's QT divided by square root of RR, okay? Just remember this. The problem that you run into, the QT prolongs a lot. You have a lot of time in the card, you know, in the electrical cycle where something can go wrong and you can go into problems with the rhythms from the ventricular arrhythmias. So that is why it is important to think about QT interval in every ECG you see, just because a lot can go wrong in that QT interval.
Yep. So not much to bother. People will definitely not be asking you this at the undergraduate level. But if you understand this number is about 0.44, and if you remember one large square was 0.2, so 0.44 is practically two large squares and a little bit more than that. And if you just eyeball the ECG, and if you find that from the beginning of the Q wave to the end of the T wave is more than two small squares, 2.5 small squares, then you're in trouble and you need to explore this further. And then you start calculating the QT corrected and thinking more about it.